Before anything else tonight, before a single fact about the universe, let yourself notice the moment you are in. Not the day, not the hour on any clock, but this exact sliver of experience, the one that feels like the front edge of your life, the place where everything is happening. You are here, in it, right now. There is a soft sense of the present pressing forward, of one instant giving way to the next, of a small bright line called now that seems to slide gently through your evening the way a needle slides through cloth. Of all the things you might doubt as you lie there, this feels like the last one you would ever give up. The past is a memory, a little faded. The future is a guess, not yet arrived. But the now, the living now, seems as solid and certain as the weight of your own body against the bed. And notice how far that now seems to reach. Without ever quite thinking it through, you carry a quiet assumption that this very instant, this present you are in, stretches out across the whole world and beyond it. You feel that while you lie here, it is also right now on the far side of the earth, and right now on the moon hanging over some other sleeper's window, and right now around the most distant star you have ever seen. A single shared presence sweeping across the entire cosmos, everyone and everything riding the same moving edge of time together. It is such a natural thought that it hardly feels like a thought at all, more like the plain shape of reality. Hold on to it gently though, because that innocent assumption, the shared now stretched across the universe, is one of the very first things we're going to watch come quietly apart tonight, and its coming apart is where the wonder begins. Hold that certainty lightly for a moment, because here is the quiet strangeness we're going to sit with tonight. That flowing now, that sense of time passing, the single most immediate fact of being alive, is nowhere to be found in the deepest descriptions physics has ever written of the world. Open the fundamental equations, the ones that govern motion and light and matter, the ones tested to more decimal places than almost anything humans have ever measured, and you will not find a now in them anywhere. You will not find a moment that is specially lit up as the present. You will not find any flowing, any passing, any movement of time at all. The mathematics knows only a fixed and patient order of befores and afters laid out all at once, like a landscape seen from very high up, with no single point marked as here and no direction marked as onward. The thing you are most sure of, the thing you are sitting inside this very second, is the one thing the world's most precise account of reality cannot seem to locate. So we have two facts, and they do not sit easily together. The first is that time passing is the most vivid feature of your inner life. The second is that time passing does not appear in the physics, and the question that opens between them, the question we will follow gently all the way to sleep tonight, is a simple one to ask and a strange one to answer. Is time real, out there in the world, a genuine feature of the cosmos, part of the furniture of reality itself? Or is the flow of it, the passing of it, the whole felt river of before and after and now, something closer to a thing your mind is doing, a shape your brain lays over a reality that, at its foundation, may not flow at all? Welcome. I'm glad you are here, at the end of your day, ready to let a large and beautiful question carry you toward the rest. This is Deep Field, where we take a single true thing about the universe and turn it slowly in the dark, not to solve it or to win an argument, but to feel the pleasure of not quite knowing, which is one of the gentlest pleasures there is. You do not need to follow every thread. You do not need to stay awake to the end. If you drift off somewhere in the middle of it, that is not a failure. That is the whole idea. Let the voice be a low light left on in another room. Let the ideas move through you the way a slow tide moves through a harbour at night, lifting the boats a little and setting them down again, asking nothing of them. We are going to pick up time the way you might pick up a smooth stone from a riverbed, and we are going to turn it over and over in the hand, looking at one face at a time. There is the face of time you feel, the private now that seems beyond all argument. There is the face of time you measure, the second on the clock counted out by machinery of astonishing delicacy. There is the face of time that Einstein turned, the one where the present stops being something everyone can share. There is the face where the laws of physics run just as happily backward as forward, and the strange fact that most of them cannot tell you which way is which. There is the face where time finally gains a direction, not from the great laws but from heat and disorder. And there are the deeper faces, the ones physicists are still arguing about softly among themselves, where time thins out and flickers, and in one of our best guesses at the foundation of everything disappears from the equations altogether, only to reappear, somehow, as the very thing you feel right now. Each of these faces answers our question a little differently. Some of them say the now is real. Some of them say it is a story you tell yourself, and by the time we have turned the stone all the way around, the question itself will have quietly changed shape in your hands, which is often what happens with the deepest questions when you hold them long enough. So settle in, let your shoulders drop. There is no hurry at all tonight, and time, of all things, is not going anywhere. Or perhaps it is going everywhere, all at once. That is rather the point. Let us begin with the face of time that feels closest, the one behind your own eyes, and then let us ask the first hard question about it. If the present moment is so certain, so undeniable, so obviously here, then why is it that no instrument ever built can point to it and say, there, that is now? A clock cannot do it. A clock does not measure the present. A clock only counts, and that gap between what you feel and what a clock actually does is the first loose thread we are going to pull. Think about what a clock truly is, underneath the face and the hands and the numbers we have painted on it. Strip all of that away, and every clock that has ever existed does exactly one thing. It finds something in the world that repeats itself over and over with great regularity, and it counts the repetitions, that is all. A clock is a counter attached to a heartbeat. The heartbeat can be almost anything, as long as it beats evenly. It can be the swing of a weight on a string. It can be the drip of water from a vessel with a small hole in the bottom, which is how some of the earliest clocks in the ancient world kept their hours, the slow fall of water measured against the slow fall of the day. It can be the shadow of a stick creeping across the ground as the sun wheels overhead, which is a clock whose repeating heartbeat is the turning of the whole earth. Every one of these devices takes some steady rhythm and tallies it, and we agree to call a certain number of those beats a minute, and a certain number of minutes an hour, and we build our lives on the counting. For most of human history, the finest clocks were tied to the sky. The day was the turning of the earth. The month was the cycle of the moon. The year was the long circuit of the earth around the sun, though no one at first knew that was what it was. These are good clocks in the sense that they are steady, but they are stubborn clocks. You cannot carry the sun in your pocket. You cannot bring the wheeling stars into a workshop and use them to time a small and delicate thing. So the great question of practical timekeeping for centuries was how to build a heartbeat you could hold in your hand, a rhythm that was your own and yet as faithful as the heavens. Long before the pendulum, people reached for whatever steady trickle of the world they could find. In ancient Egypt and later in Greece, water clocks did the counting. Vessels of water with a small opening through which the water fell drop by drop, the level sinking at a steady rate that could be marked off against the hours. These were among the first machines that let people measure time indoors, away from the sun, through the night, in a courtroom to limit how long a speaker could hold the floor, in a temple to time the rituals of the dark. The Egyptians also read the day from shadow, using the long finger of a slanted stone to track the sun across the sky, dividing the daylight into a set of hours, and the night into another set marked by the rising of particular stars. But here is a curious thing about those ancient hours that shows how strangely time can be sliced, because they cut the daylight into a fixed number of parts, and the darkness into a fixed number of parts, and because the length of day and night swings with the seasons, their hours were not all the same length. A daytime hour in high summer, with its long stretch of light, was a good deal longer than a daytime hour in the deep of winter. Time was measured, but it stretched and shrank with the turning year. An hour that was not quite the same hour from one month to the next. It took a very long climb and a great deal of ingenuity before humanity insisted on an hour that was always the same length, a beat that did not care what season it was, and to get there we needed a better heartbeat than falling water. The answer that changed everything came from a Dutch mathematician and astronomer named Christian Huygens in the 1650s. Huygens took an old observation, one that the aging Galileo had noticed and puzzled over, that a swinging weight seems to take the same amount of time to complete its swing whether the swing is wide or narrow. A pendulum, in other words, keeps a remarkably even beat. Huygens saw how to harness that. He designed a clock in which a swinging pendulum released the movement of gears one small step at a time, tick following tick, each tick the same length as the last, and suddenly humans had a heartbeat of their own making that could keep pace with the day to within a handful of seconds. Before Huygens, the best mechanical clocks might wander by a quarter of an hour or more across a single day. After him, the error shrank to seconds. It was one of the great quiet leaps in the history of measurement, and it happened because one careful man understood that time, for a clock, is nothing more than a good steady swing counted honestly. But notice what has slipped past us here, because it matters for our question. Huygens did not build a machine that captures the flow of time. He built a machine that counts a repeating event. The pendulum does not know that time is passing, it simply swings, and something else counts the swings. If you were to ask the clock where the present moment is, it would have no answer, because the present is not among the things it measures. It measures duration, the gap between one tick and another, the interval between events. It has nothing at all to say about which tick is happening now. Every tick to the clock is exactly like every other. The now is our addition, not the machine's. The story of clocks after Huygens is a long climb towards steadier and steadier heartbeats, and it is worth walking a little way up that climb because it tells you something about how deep this idea of counting goes. The pendulum gave way in time to the balance wheel and the hairspring, which let a clock keep good time even on the rolling deck of a ship. And that was no small thing, because a sailor who knew the exact time could work out how far east or west he had travelled, and countless lives were saved by clocks accurate enough to find longitude at sea. Then came the quartz crystal, a small sliver of mineral that, when a little electricity has passed through it, vibrates with a rhythm so even that a wristwatch built around it might drift by only a second across many days. The quartz in a cheap watch on a bedside table is counting tens of thousands of its own tiny shivers every second, faithfully, silently, while you sleep. It is worth pausing on that step from the pendulum to a clock steady enough to carry on a ship, because it was one of the hardest and most consequential problems of its age, and solving it was a matter of life and death. For centuries, a captain far out at sea could find how far north or south he was easily enough by measuring the height of the sun or the pole star. But how far east or west he had come, his longitude, was a torment, because working it out required knowing, at the same instant, both the local time where the ship was, read from the sun overhead, and the time back at the home port he'd sailed from. The difference between the two would tell him how far around the world he'd travelled. But no clock of the day could keep true time through months of pitching seas, changing temperatures and salt air. Ships were lost by the hundreds, whole fleets wrecked on coasts their navigators had badly misjudged, and a great prize was offered to anyone who could solve it. The man who did was a self-taught English clockmaker named John Harrison, who gave much of his life to the problem across the middle of the 1700s, building a series of extraordinary sea clocks that used cleverly balanced springs and metals that compensated for heat and cold, until at last he made a timekeeper that could cross an ocean and lose only a few seconds along the way. With that, a captain could carry the time of a home in a box and always know where on the turning earth he stood. A clock, once again, had changed the map of the world, and it did so by being nothing more than a very faithful counter of a very steady beat. And then, in the middle of the last century, timekeepers reached for the steadiest heartbeat in all of nature, the atom itself. Deep inside a cesium atom there is a rhythm, a natural oscillation between two states of the atom that beats with a regularity beyond anything a swinging weight or a shivering crystal could offer. Count that rhythm, and you have the finest clock humanity has ever made. In the year 1967, the world scientists agreed to redefine the second itself in terms of that atomic beat. They chose a number, a very large and specific number of oscillations of the cesium atom, and declared that when the atom has beaten that many times, 1 second has passed. The number is close to 9 billion. Let that settle for a moment. When you say the word second softly, 1 second, the cesium atom at the heart of the world's clocks has trembled through something like 9 billion beats. A bell struck 9 billion times in the space of one slow breath. The very finest atomic clocks now keep time so well that they would neither gain nor lose a single second across many millions of years, longer than our species has existed, longer than there have been forests on the land. It is worth resting for a moment on what happens inside such a clock, because it is quietly wonderful. The clock coaxes the cesium atoms with carefully tuned radiation, and listens for the exact rhythm at which they respond most strongly. the atom's own natural note, and it keeps adjusting itself to stay perfectly in tune with that note, using the atom as the tuning fork against which all its counting is checked. Because every cesium atom in the universe shares exactly the same natural rhythm, unchanging, identical, whether it sits in a laboratory in one country or another, or drifts in a cloud between the stars, this gives us a standard of time that is not tied to any one place or any one object, but is woven into the very fabric of matter itself. That is why the world could agree to define the second this way. When the timekeepers chose that great number of oscillations to stand for 1 second, they were not inventing time, they were pinning our human unit to a rhythm nature offers freely everywhere, the same for all. And still, for all the depth of that, the clock is doing nothing our first water clock did not do. It waits for a repeating beat, and it counts. The rhythm is now the trembling of an atom rather than the falling of a drop, counted billions of times faster and immeasurably more faithfully. But the act is identical, and the silence on the question of the present is identical too. And the newest clocks are steadier still, so steady that they have begun to reveal something about time that we will come back to again and again tonight. These are clocks built not around the cesium atom but around other atoms held almost perfectly still in a web of laser light. Their beat read not in billions but in hundreds of trillions of oscillations each second, a heartbeat faster and finer than anything humanity has ever counted. They have grown so precise that they can measure a difference in the flow of time across a height you could span with your open hand. Raise one of these clocks a small distance above another, no more than the width of a book, and the higher clock will run very slightly faster than the lower one, and these instruments can now see that difference. Time, it turns out, runs a shade quicker for your head than for your feet as you stand, quicker on a shelf than on the floor, and the reason is gravity, which we'll come to soon. For now, simply hold the strangeness of it. We built a clock so good that it stopped merely keeping time and started showing us that time itself is not one single thing everywhere, that it runs at its own private rate at every different height and speed. The counter, perfected almost beyond belief, became a window onto the fact that the thing it counts does not flow the same for everyone, and that fact was first uncovered not by a clock at all, but by a young man thinking very hard about light. That is a staggering achievement, and it is worth resting in for a breath. We began with a shadow crawling across the dust, and we arrived at a rhythm buried in the structure of an atom, counted billions of times a second, and yet, for all that delicacy, notice that nothing has changed about what a clock fundamentally is. The atomic clock is still only a counter attached to a very good heartbeat. It counts the beats of the cesium atom exactly as the old water clock counted the falling drops. It is faster and steadier by a factor almost too large to picture, but it is doing the very same thing. It measures how many beats fall between two events. It says nothing whatsoever about which beat is now. The most precise clock ever built is as silent as a sundial on the question that started us tonight. It can tell you the interval between this moment and that one to a breathtaking number of decimal places. It cannot tell you, and does not even try to tell you, which of those moments is the living present. So the machinery of the clock in all its beauty gives us our first real hint. When we measure time, we are not measuring a flow. We are counting repetitions and reading off intervals. The counting is real, the intervals are real, the atom's beat is as real as anything in this world. But the passing, the flowing, the moving now, is not something the clock ever touches. It sits, so far, entirely on our side of the glass in the watcher and not in the watched. That might be a small quirk of clocks, or it might be the first sign of something much larger. To find out which, we have to leave the workshop and follow this thread into the strangest and most beautiful revolution in the history of physics. The moment when a young man in a patent office looked hard at the nature of time and discovered that the present, the shared, now we all assume we live inside together, does not exist in the way we thought. That is where we turn next. For more than 200 years, the picture of time that most people carried, and that physics itself carried, was the one drawn by Isaac Newton. Newton wrote, near the beginning of his great work on motion, that absolute time flows equably without relation to anything external, and that it flows of its own nature at a constant rate throughout the universe. It is worth hearing what that means, because it is almost certainly the picture you grew up with, whether or not anyone ever spelled it out for you. Newton was saying that time is a kind of universal river, the same river everywhere, flowing at the same rate on the surface of the earth, and in the depths of space, and in the heart of the sun, carrying every event along together. On this picture there is a single cosmic now, a present moment that stretches across the entire universe at once. If it is this instant here, then it is this same instant on the moon, and around the most distant star, and everywhere. The whole cosmos shares one clock, one flowing present, ticking in step. It is a calm and orderly and deeply intuitive idea. It also happens to be wrong, and the person who showed that it was wrong did so at the age of 26, working in the evenings, employed by day as a clerk examining patent applications in the Swiss city of Bern. His name was Albert Einstein, and the year was 1905, a year in which he published several papers that each, on their own, would have made a career, and one of which quietly dismantled Newton's universal river. Einstein had been troubled by a puzzle about light. Other physicists had worked out, from the equations describing electricity and magnetism, that light travels at a particular speed, close to 300,000 kilometers per second, a speed so great that a beam of it could circle the Earth about 7.5 times while you finished a single slow breath. But the equations had a strange feature. They gave that one speed for light without saying what the light was moving relative to, and every other speed we know is relative to something. A person walking down the aisle of a moving train travels at a gentle pace relative to the train, but at the train's full speed, and more relative to the fields outside. Speed, in ordinary life, always depends on who is asking. Light seemed to refuse that. Its speed came out the same in the mathematics no matter how you chased it. For a long time, physicists tried to make this puzzle go away with an idea that seemed only sensible. Every other wave they knew of needed something to travel through. Sound waves need air, ripples need water, a wave on a rope needs the rope. So surely light, being a wave, needed a medium too, some invisible substance filling all of space, through which light rippled the way sound ripples through air. They called this supposed substance the luminiferous ether, the light-bearing ether, and they were confident it must be there, an unseen sea in which the Earth and all the stars were swimming, and it made a clean prediction. If space is filled with this ether, and the Earth is racing through it in its orbit around the Sun, then there should be a kind of wind of ether streaming past us, and light sent in the direction of that wind should travel at a measurably different speed than light sent across it, just as a swimmer moves faster with a current than across it. In the 1880s, two American scientists, Albert Michelson and Edward Morley, built an instrument of exquisite sensitivity to catch that difference, splitting a beam of light and sending its halves along two paths at right angles, then bringing them back together to compare their timing with great delicacy. They expected to measure the Earth's motion through the ether, and they found nothing. No difference at all. Light travelled at exactly the same speed in every direction, as though there were no ether wind, no current, no invisible sea. It was one of the most famous failed experiments in history, a beautifully designed search that came back empty, and it left physics with a deepening crisis, because the thing everyone was sure must exist appeared not to exist, and light's stubborn refusal to change its speed had no explanation at all. Einstein made a bold and beautiful decision. Instead of treating this as a problem to be explained away, he took it as a law of nature and asked what the universe would have to be like for it to be true. He proposed two simple starting points. The first was that the laws of physics are the same for everyone moving smoothly and steadily, that there is no special stationary place in the universe against which all motion is measured, that a traveller gliding through space with the curtains drawn could perform no experiment to tell whether they were moving at all. The second was that the speed of light in empty space is the same for every such observer, no matter how fast they themselves are moving toward the light or away from it. These two ideas sound almost modest. Their consequences are anything but. Follow it gently with me. Suppose the speed of light is truly the same for everyone. Speed is just distance divided by time, how far something goes divided by how long it takes. If two people moving differently must both measure light's speed as the same value, and they disagree about the distances involved, which they will if one of them is moving, then they must also disagree about the times. There is no other way for the arithmetic to balance. To keep the speed of light fixed for everybody, space and time themselves have to bend and stretch and slide from one observer to the next. And the first casualty of that bending is the one thing Newton was surest of, the shared present. Once you accept Einstein's two starting points, you are forced to conclude that two events which happen at the same time for one person can happen at different times for another. Simultaneity, the very idea of two things happening now together, comes apart in your hands. Einstein pictured it with a train, and the picture is so clear it has been passed down for over a century. Imagine a long carriage moving smoothly along a track, and imagine two flashes of lightning striking the ground, one at the front of the carriage and one at the back, in such a way that a person standing beside the track, exactly halfway between the two strikes, sees both flashes reach their eyes at the very same instant. For that person on the ground, the two strikes were simultaneous. They happened at the same now, but now think of a passenger sitting in the exact middle of the moving carriage. During the tiny time the light from each flash takes to travel, the carriage carries this passenger forward, toward the flash at the front and away from the flash at the back. So the light from the front reaches the passenger a fraction sooner and the light from the back a fraction later. The passenger, seeing the front flash first, concludes with perfect logic that the lightning struck the front before it struck the back. The two strikes were not simultaneous for the passenger at all, and here is the part that unsettles Newton's whole universe. Neither of them is mistaken. There is no experiment, no cleverer measurement that could reveal which of them is right about the true order, because there is no true order. Whether two separated events happen at the same time is not a fact about the universe. It is a fact about your motion. The present is not shared. Each of us, depending on how we move, slices the great block of events into now and not yet along a slightly different angle. Before we go deeper into what that does to the flowing now, let me pause for just a moment, because this is a channel that runs quietly, without a great deal of noise around it, and it grows only when someone who's enjoying it decides to let it grow. If tonight's slow turning of ideas is the kind of thing you would like to have waiting for you tomorrow night, and the night after, you might consider subscribing, not as a favour to me so much as a small kindness to a calm corner of the world that would like to keep the lights on. That is the only time I will mention it. Now let your attention loosen again, and come back to the strangeness of a present that bends with your motion, because relativity did not stop at unsettling simultaneity. It went on to do something even stranger to the passing of time itself. If observers moving differently disagree about which events are simultaneous, they must also disagree about how much time passes between events, and they do. A moving clock, seen from a place it is moving relative to, runs slow. This is not an illusion, not a trick of the eye, not a matter of the clock appearing to run slow while secretly keeping true time. The slowing is as real as anything measured in a laboratory. You can see why it must happen with a simple picture, a clock made of light. Suppose you build a clock from two mirrors, one above the other, with a single pulse of light bouncing straight up and down between them, and you call each round trip one tick. When this clock sits still beside you, the light goes straight up and straight down, the shortest possible path tick after even tick. But now let the whole clock glide past you at great speed. From where you stand, the light no longer travels straight up and down, because between leaving the bottom mirror and returning, the clock has moved sideways. So the light, from your point of view, must travel along a longer slanted zigzag path to make the same round trip. And since the speed of light is fixed, always the same for you, light that has farther to go must take longer to get there. The moving clock's ticks, seen by you, are spaced farther apart. Its time runs slow. The faster it moves, the slower it runs, and the effect grows without limit as the speed climbs toward the speed of light. And time is not the only thing that bends. Hand in hand with the slowing of moving clocks comes a shrinking of moving lengths. An object rushing past you is measured by you, as shortened along its direction of motion, squeezed a little in the way it travels, and the faster it goes, the more it shrinks. Two physicists, an Irishman named George Fitzgerald and a Dutchman named Hendrik Lorentz, had guessed at this contraction before Einstein, proposing it as a desperate patch to explain why the ether experiment had failed, though they did not yet see the full and simple truth beneath it. That truth is that space and time are not the fixed and separate stages we imagine. They give a little, both of them, to keep the speed of light the same for everyone, trading against each other as your motion changes. You can even feel this trade in the raining ones we will meet in a moment. From our point of view on the ground, the Mon survives its long fall because its internal clock runs slow. But from the Mon's own point of view, its clock runs perfectly normally, and it lives its usual brief life. What saves it, in its own telling, is that the thick blanket of atmosphere it must cross is, for something moving so fast, dramatically contracted, squeezed thin, so that the long fall becomes a short hop it can finish before it decays. Two different stories, the slowed clock and the shortened distance, and both are true, each from its own vantage, and they always agree in the end about what actually happens. That is the deep harmony hiding inside all this strangeness. Observers disagree about times and about lengths, but never about the events themselves. For a long time, this stayed a matter of thought, experiments, and elegant equations, and one could be forgiven for suspecting nature might not really behave so strangely, but nature does, and we can watch it. High in the atmosphere, when particles from deep space crash into the thin upper air, they create showers of tiny particles called muons, which are heavy cousins of the electron. A muon is a fleeting thing. Left to itself, at rest, it survives for only about 2/millionths of a second before it decays into other particles. Travelling at the tremendous speeds these muons have, even at the speed of light they should manage only a few hundred meters before their brief lives run out, nowhere near enough to reach the ground far below. And yet the ground is thick with them. Detectors at sea level catch muons pouring down in great numbers, muons that by all rights should have died in the high air. The reason they reach us is time dilation. Moving so fast relative to the Earth, their internal clocks, the little countdowns to their own decay, run slow from our point of view, slow enough that their 2/millionths of a second stretches into enough time to complete the long fall. Physicists first measured this effect carefully in the 1940s, and again with great precision in the 1960s, and the numbers matched Einstein's mathematics. The muons are living proof, raining down on your rooftop right now, that time itself runs at different rates for things moving differently. If that still feels too exotic, consider that you carry the consequences in your pocket. The satellites that let a phone find its place on the Earth work by broadcasting the time from clocks on board, and a receiver on the ground compares the timing of signals from several of them to work out where it is. Those satellite clocks are moving fast, high above us, and the effects of relativity are large enough that if they were ignored, the whole system would drift off by a growing error every day, until within a short time it would place you streets away from where you actually stood. The engineers who built it had to teach the satellites to account for the fact that their onboard clocks and the clocks on the ground do not agree, that time up there and time down here run at subtly different rates. Every time a map on a screen shows a small blue dot resting exactly where you are, it is because someone took Einstein's strange claim about time perfectly seriously and built the correction into the machine. The relativity of time is not a curiosity kept in a textbook. It is a working part of the modern world, checked and confirmed 1 billion times a day. There was a moment in the year 1971 when this stopped being a matter of tiny particles and satellite arithmetic, and became something you could do with ordinary clocks and an airline ticket. Two scientists, Joseph Haffel and Richard Keating, took atomic clocks, real portable versions of the finest timekeepers of their day, and simply flew them around the world aboard commercial airliners, first heading east, then heading west, while an identical clock stayed behind on the ground. When the travelling clocks came home and were compared to the one that had stayed, they no longer agreed. They had drifted apart from the ground clock by tiny fractions of a second, and by just the amounts that Einstein's mathematics predicted, accounting for both the speed of the aircraft and the height at which they flew, where gravity is a touch weaker and time runs a touch faster. Clocks that had flown were now permanently out of step with clocks that had stayed home. The travellers had, in the most literal and measurable sense, aged by a slightly different amount than those who remained. It was a small difference, far too small to feel, but it was real, and it had been carried around the world in the luggage rack of an ordinary plane. Push that idea to its limit and you arrive at one of the most haunting consequences of relativity. A thing so strange it is often mistaken for a paradox, though it is simply the truth. Picture two twins, born on the same day, alike in every way. One of them stays home on the Earth, living an ordinary life. The other boards a ship that can travel at a great fraction of the speed of light, journeys out to some distant star, turns around, and comes home. Because the travelling twin has been moving so fast, their time has run slow relative to the twin who stayed. Not as an illusion, but real, so that when the ship finally lands, the two are no longer the same age. The The traveller steps out, having felt only a few years pass, perhaps still young, and is met by a twin who has lived out decades, grown grey, grown old. They were born on the same day, and now one is old and one is young, and neither of them is mistaken, and no clock anywhere was faulty. The difference is real and permanent, written into their bodies, their memories, their faces. Time truly ran at different rates for the two of them, and the gap does not close. It is one thing to read that moving clocks run slow. It is another to feel what it would mean to embrace a brother or sister who left when you were both children, and returned, from their side, only a little while later, while your whole life had slipped past in their absence. That is the reality relativity insists upon, and it is not a trick of the equations but the plain way the world is built. There is no single universal now for those two lives to share, and there never was. There is one more turn to this chapter, and it plants a seed we will return to near the end of the night. A few years after Einstein's work, a mathematician named Hermann Minkowski, who had once been Einstein's teacher, saw a way of understanding all this that was even deeper than the equations first suggested. If observers disagree about space, and disagree about time, but always agree about the events themselves, then perhaps space and time are not two separate things at all, but two aspects of a single unified thing, which we might call space-time. Minkowski proposed that we stop thinking of space as a stage and time as a river flowing over it, and instead think of a single four-dimensional whole in which every event has its fixed address, and different observers merely carve that one whole into their own space and their own time along their own angles. He announced this with a famous and rather beautiful declaration, saying that from then on space alone and time alone were doomed to fade into mere shadows, and only a union of the two would preserve any independent reality. It was a poetic way of saying something that will grow heavier as our night goes on. If space and time are woven into one fixed four-dimensional fabric, then all the events of history and all the events still to come may already be laid out together in that fabric, complete, like a landscape with no flowing river running through it at all. But we are getting ahead of ourselves. Hold that thought lightly for now, and let us step back from relativity to ask a blunter question of the other great laws of physics. So the second face of time, the one Einstein turned, tells us something remarkable, and now beyond serious doubt. There is no single universal now. The present is sliced differently by everyone in motion. Time can run fast or slow depending on how you travel. Newton's calm universal river is gone, replaced by something far more intricate and far more beautiful. And yet, and this is the thread we must carry forward, notice that even in all this strangeness, we still have not found the flowing. Relativity tells us that clocks disagree, that presents differ, that time stretches. But nowhere in Einstein's equations does time move. The equations describe a fixed pattern of events spread through space and time together, and they let us calculate how any observer will slice that pattern. But the slicing is ours. The pattern itself just is. Relativity took the shared now away from us, and in doing so it left the passing of time looking more and more like something that happens in observers, and less like something that happens in the world. To see how far that suspicion goes, we have to look at the great laws of physics directly and ask them a blunt question. Do any of you even know which way time is supposed to go? And the answer, from almost all of them, is no. Set aside relativity for a moment and look at the other pillars of physics, the laws that describe how things move and change from one instant to the next. There is the great law of motion at the heart of classical mechanics, the one that tells you how a force changes the movement of a mass, the workhorse that carries a thrown ball through its arc and holds the planets in their orbits. There are the laws of electricity and magnetism, written by James Clerk Maxwell in the 1860s, which describe how electric and magnetic fields ripple and give rise to light. There is the central equation of quantum mechanics, discovered in the 1920s, which governs how the ghostly wave that describes a particle evolves. These are the crown jewels of physics, the deep rules underneath nearly everything, and they share a feature that is easy to state and very hard to feel, a feature that goes to the heart of our question tonight. Almost every one of them works exactly the same whether time runs forward or backward. Here is what that means, plainly. Suppose you filmed some purely physical event governed by these laws, and it was a clean, simple event, A single ball rolling and bouncing off a wall in empty space, or two billiard balls colliding and springing apart, or a planet swinging around a star. Suppose you then ran the film backward and showed it to a physicist without telling them which way it was playing. In the great majority of cases, they could not tell. The backward film would show motion that obeys the same laws just as perfectly as the forward film. A ball rising and slowing and falling looks like a ball falling and speeding and rising, and both are exactly what the law of gravity permits. Two balls flying apart after a collision run in reverse, become two balls flying together into a collision, and that too is a perfectly lawful thing to happen. The equations do not contain a little arrow that says this way is the future. They describe a set of allowed patterns, and for almost every allowed pattern, the time-reversed version is equally allowed. Physicists have a name for this. They call the fundamental laws time-symmetric, or time-reversal invariant, and it is one of the most quietly astonishing facts in all of science. Honesty requires one small note here, and it is a beautiful wrinkle rather than an escape. The symmetry is not quite perfect. Deep in the behaviour of certain rare particle interactions, in the workings of the weakest of nature's forces, physicists have found a tiny, delicate asymmetry, a whisper of a difference between the forward and backward directions, so that in a few exotic processes nature does, ever so slightly, tell one way apart from the other. It is a genuine and fascinating discovery, and it hints at deep matters, perhaps even at why the universe contains matter at all rather than nothing. But it is far, far too small and too rare to account for the overwhelming one-way rush of ordinary time. It cannot explain why your coffee cools, why glass shatters and never mends, why you remember yesterday and not tomorrow. That vast everyday arrow, the one that shapes every second of your life, is simply not there in the fundamental laws in any form remotely strong enough to produce it. The tiny exception only sharpens the mystery rather than solving it. The great directionless symmetry of the deep laws still stands, staring back at the utterly directed world of your experience, and the gap between them still cries out for an answer that the laws of motion, tiny wrinkle and all, cannot give. It is astonishing because it flatly contradicts your entire experience. Your whole life is a one-way street. You remember the past and not the future. You grow older and never younger. A cup that slips from a table shatters on the floor, and you have never once seen the shards leap up, gather themselves, and reassemble into a whole cup that rises gently back to your hand. Cream stirred into coffee, spreads and mingles and never unmixes. Heat flows from the warm thing to the cool thing and never the other way, so that a hot drink left alone always cools toward the temperature of the room, and a cold drink always warms toward it, and never, ever the reverse. Everywhere you look, time has an obvious and overwhelming direction, and yet when you go down to the deepest laws that govern the pieces, the atoms and the fields and the forces, that direction simply is not there. The laws are as content to run one way as the other. Where then does the arrow come from? If the rules of the game do not care which way time flows, why does the game so plainly flow one way for us? For a long time this was a real confusion, and some very good thinkers assumed the arrow of time must be built into the basic laws somewhere, hidden, waiting to be found, because surely a fact as obvious as the difference between past and future had to live at the foundation. That assumption turned out to be a mistake, and it was a fruitful mistake, because chasing it down led to one of the most profound discoveries of the 19th century. The direction of time, it turns out, does not come from the deep laws of motion at all. It comes from somewhere else entirely, from counting, from probability, from the overwhelming likelihood of disorder, and from a single strange fact about how our universe happened to begin. To understand where the arrow of time is hidden, we have to leave the clean world of frictionless balls and perfect equations, and step into the warm, messy, magnificent science of heat. The science of heat was born, appropriately enough, from fire and iron and the hard practical problem of making engines work. In the early 1800s, steam engines were transforming the world, and engineers wanted to know the rules of the game, how much useful work you could squeeze from a given amount of heat, and why an engine could never be perfect. A young French engineer named Sadi Carnot thought his way through this with great care, and laid the first stone, showing that there were absolute limits to what heat could do, limits set not by clumsy engineering but by nature itself. Building on that foundation, a German physicist named Rudolf Clausius, in the year 1865, gave the crucial idea its name. He called it entropy, from a Greek root meaning transformation, and he stated the law that has haunted and delighted physicists ever since. In any closed system, one that nothing enters or leaves, entropy never decreases. It can hold steady, in an ideal and impossible case, but in the real world it always climbs. This is the second law of thermodynamics, and it is the closest thing physics has to a law with a built-in direction. Heat flows from hot to cold. Order gives way to disorder. Things run down. The second law is the reason your coffee cools and never spontaneously reheats, the reason a dropped glass shatters and never reassembles, the reason, in the end, for the whole one-way feeling of time. But what is entropy, really? Clausius gave it a precise meaning in terms of heat and temperature, but the deeper understanding, the one that reaches down to our question tonight, came from an Austrian physicist named Ludwig Boltzmann, working in the last decades of the 19th century. Boltzmann saw that entropy is, at bottom, a matter of counting. Picture the air in the room around you. That air is made of an almost unimaginable number of tiny molecules, flying about, bouncing off one another and off the walls, far too many to ever track individually. Now, there is only a small number of ways for those molecules to be arranged so that all the air is bunched into one corner of the room, leaving the rest a vacuum. But there is a colossal, overwhelming number of ways for them to be spread evenly throughout the whole room, which is what we always find. Boltzmann's insight was that what we call a low entropy state, an orderly state, is simply one that can be made in very few ways, and a high entropy state, a disordered state, is one that can be made in fantastically many ways. And since the molecules are jostling about at random, blindly, with no plan, they are overwhelmingly likely to stumble into one of the many disordered arrangements, rather than one of the few orderly ones, purely because there are so many more of them to stumble into. That is the whole secret of the arrow of time, and it is worth pausing to feel how strange and how satisfying it is. The reason time seems to flow from order to disorder is not that some law forbids the reverse, it is that the reverse is not forbidden, merely staggeringly unlikely. Watch a drop of dark ink released into a glass of still, clear water. It uncurls and spreads and thins, reaching out in soft tendrils until the whole glass is an even pale grey, and it never, in all your life, gathers itself back into a single dark drop. There is no law that would be broken if it did. Every individual molecule of ink retracing its path would be obeying the rules of motion perfectly. It is simply that the spread-out arrangement can happen in so many more ways than the gathered one that, given random jostling, the ink spreads and stays spread, and the gathering, though not impossible, would require a coincidence so vast you could watch 1,000 universes live and die and never see it once. The arrow of time is written in probability, not in law. It points the way it does because disorder is common and order is rare, and blind motion drifts, always, toward the common. To feel why order loses so completely, you have to feel how enormous the numbers really are. Take a single ordinary breath, the one you're drawing now. In that one breath, there are something like 10,000 billion molecules of air, a number so large that if you tried to count them one each second, it would take you longer than the age of the universe many times over. In fact, there are so many molecules in a single breath that, spread out and mixed through the whole atmosphere over the years, some of the very molecules you're breathing this instant were almost certainly once breathed by people who lived thousands of years ago. That is how vast the count is inside one quiet breath. Now, the number of different ways all those molecules could be arranged is a number so far beyond that as to have no name and no picture, and out of that unthinkable ocean of possible arrangements, the orderly ones, the ones with all the air bunched neatly in a corner, are the very rarest droplets, while the disordered ones, the ones spread smoothly everywhere, are almost the entire sea. When the molecules jostle blindly, they are simply lost in that sea, drifting among the countless even arrangements, with no chance at all of stumbling back to the vanishingly few tidy ones. The overwhelming force of the second law is nothing but the overwhelming weight of those numbers. Disorder wins not because it is stronger, but because there is so incomparably much more of it. Follow that drift far enough into the future and it points toward a strange and peaceful destination. If entropy always climbs, then across unimaginable stretches of time the universe should keep smoothing out, stars burning through their fuel and going dark, heat spreading from everything warm into everything cold until there is nothing warmer or colder left anywhere. Every difference evened away, every gradient gone. Physicists have long called this far-off state the heat death of the universe, though the name sounds harsher than the thing itself. It would not be fire or violence, but the opposite. A vast, lukewarm stillness in which nothing can happen anymore, because things only happen where there is a difference to drive them, and all the differences would be spent. It lies fantastically far ahead, so far that the whole age of the universe until now would be less than a blink against it, and there is genuine uncertainty about the details, since we do not fully know the ultimate fate of the cosmos. But the direction is clear enough. The same slope that lets your coffee cool and your memories form is the slope the whole universe is sliding down, from the ordered brightness of the beginning toward the even, quiet grey of the end. Every ticking clock, every living thing, every thought is a small eddy in that one long descent. Boltzmann pushed this idea so hard and defended it so fiercely against those who doubted that the world was truly made of atoms that it became the work of his life. There is a small and tender scene worth carrying with you. Boltzmann's great equation, the one relating entropy to the number of ways a state can be arranged, is carved on his gravestone in Vienna, a single line of mathematics standing in for a life's argument, placed there after his death in the year 1906. He did not live to see how completely he would be vindicated, how the reality of atoms and the truth of his statistical vision would become the settled bedrock of physics within a few years of his passing. He carried a difficult mind and a hard life, and he left the world too soon, and yet the idea he fought for turned out to be one of the deepest we have. When you watch steam rise from a cup and disperse into the air, you are watching Boltzmann's counting play out. The drift toward the many and away from the few, the quiet arithmetic that gives your days their direction. And yet there is a puzzle hidden inside this beautiful answer, and honesty requires us to name it, gently, because it is one of the genuinely open questions of physics, and it bears directly on tonight. If disorder is so overwhelmingly more likely than order, then why was there ever any order to begin with? Why is the universe not already, and always, in the bland even greyness of maximum entropy, with nothing left to run down? The only reason the second law can give us an arrow of time is that the universe started long ago, in a state of extraordinarily low entropy, an exquisitely ordered state, and has been climbing toward disorder ever since. Everything that has ever happened, every stirring of order, every living thing, every thought you have ever had, is riding on that long slow slide from the ordered beginning toward the disordered end. Physicists call the assumption that the early universe was in such a special low entropy state the past hypothesis. It fits all the evidence beautifully. The trouble is that no one has fully explained why the universe began that way. Roughly 13.8 billion years ago, in the earliest moments we can speak of, the cosmos was in a state of remarkably low entropy, and the deep reason for that remains to this day genuinely unsettled. Sit with how odd this really is, because it turns the whole arrow of time into a kind of inheritance. Everything you experience as the passage of time, every memory forming, every process running its course, borrows its direction from that ordered beginning. The past is different from the future in the end, for one reason above all others, that the past lies nearer to the low entropy beginning and the future lies farther from it, so that we are all, always, sliding away from that original order and toward the disorder ahead. But why the universe began in so special, so exquisitely ordered a state, when disorder is so overwhelmingly more likely, is one of the genuine puzzles at the frontier of physics. If you simply picked a state of the universe at random from all the states it might have been in, you would almost never get one so ordered. The beginning we had is fantastically, almost incomprehensibly untypical, a needle in a haystack the size of everything, and no one is certain why. Some physicists suspect the answer lies in the physics of the universe's earliest instance, in processes we do not yet fully understand. Others wonder whether our whole visible universe is a small and unusually orderly patch of something far larger. These are open questions, real and unsettled, and I will not pretend otherwise. But the shape of the answer we do have is already remarkable enough. The reason time seems to flow, the reason there is any direction to your days at all, traces back not to a law but to a condition, a fact about how things happen to start, an ordered dawn whose light we are all still, quietly, falling away from. Physicists do not yet agree on it. That is not a failure to be embarrassed by. It is a live and beautiful edge of what we know, and it means that the arrow of time, the very directedness of your experience, rests on a fact about the beginning of everything that we can measure but cannot yet explain. So the third face of time, the thermodynamic face, has given us something the great laws could not. It has given us a direction. It has told us why the past differs from the future, why you remember one and not the other, why things wear and spread and cool and never spontaneously repair. That is real. That is settled. The arrow of time is not an illusion, but look closely at what kind of thing this arrow is, because here we arrive at the turning point of our whole night. The thermodynamic arrow is a direction, a gradient, a slope from order to disorder laid out across the block of events. It tells you which way is downhill. But a slope is not a river. A direction is not a flow. The second law tells you that entropy is lower over there, in what we call the past, and higher over there, in what we call the future. It does not, anywhere, describe a moving now sliding along that slope. And this is the thing I've been quietly leading you towards since the first minute of tonight. The loose thread we have been pulling all along, now finally coming free in the hand. Gather up everything we have turned over so far. The clock does not measure a flow, it only counts intervals. Relativity abolishes the shared present and lets time run at different rates for different travellers, but its equations describe a fixed pattern of events, not a moving one. The fundamental laws of motion do not even contain a direction of time, running as happily backward as forward, and thermodynamics, which finally gives us a direction, gives us only a slope of probability across a landscape of events, not a current moving through it. Step back and look at the whole picture that physics has drawn, and here is what you find. There are events, arranged in a definite order, spread throughout space and time. There is a direction to that arrangement, from low entropy toward high, and that is all. There is no moving spotlight of the present picking out one moment as now. There is no flowing, no passing, no becoming. All the moments simply are laid out together, the way all the places in a landscape simply are, whether or not you happen to be standing in them. A philosopher gave this puzzle its sharpest shape more than a century ago, and his way of splitting it has quietly shaped every conversation about time since. His name was John McTaggart, and in the year 1908 he pointed out that there are two very different ways to order the events of the world in time. One way sorts them into past, present, and future. On this way of ordering, a certain event is future for a while, then becomes present, then slides off into the past, and this ordering is always changing, because what is present keeps moving. This is the tensed way, the flowing way, the way that needs a moving now. The other way sorts events only by which came earlier and which came later. Your birth is earlier than this moment, and this moment is earlier than your 100th birthday, and these relationships never change and never move. This is the tenseless way, the fixed way, an ordering with no now in it at all, no flowing, only the permanent pattern of before and after. McTaggart's startling claim was that the first ordering, the flowing one we feel so strongly, cannot be a fundamental feature of reality because it tangles itself in contradiction the moment you look at it closely, while the second, the fixed ordering, though real, contains no passage of time whatsoever. Whether or not he was right in every step of his argument, and philosophers still contest it, he had put his finger on exactly the gap we keep finding. Physics describes the world beautifully in the second way, the fixed pattern of earlier and later, and it says nothing at all in the first way, the moving present. The flow is precisely the part that will not fit into the pattern, and McTaggart saw that clearly, long before the physics had made the absence so stark. Think of a novel, already written, already printed, sitting closed on a table. Every page exists at once, the first and the last and all the pages between, the whole story complete and present in the stack of paper. When you read it, you take it in one line at a time, and as you read there is a vivid sense of a story unfolding, of a now moving through the tale, this sentence happening while the next waits ahead, and the last recedes behind. But that unfolding is in your reading, not in the book. The book does not flow. It just is, all of it, at once. The sense of a moving present belongs to the reader passing through, not to the pages, which lie there entire and unmoving whether anyone reads them or not. What physics seems to be telling us across every face of time we have turned so far is that the universe may be far more like the printed book than like the unfolding story. The events are all there, in their fixed order, with their fixed entropy slope. The moving now, the passing, the flow is not written into the pages of the world, and if it is not in the pages, then it must be in the reader. Let that settle softly for a moment. There is no need to seize it or argue with it tonight. Just let it rest against you like a cool hand. The flowing of time, the single most certain fact of your experience, the thing we began with as the last thing you would ever doubt, has quietly gone missing from the physical world as physics describes it. Not the order of events, which is real, not the direction from past to future, which is real, but the passing, the movement, the living slide of the present seems not to be out there at all. Which raises the gentlest and strangest possibility of the whole night. Perhaps the flow of time is not something the universe does. Perhaps it is something you do. Perhaps the river is not in the world but in the watching. And if that is so, then to understand the flow of time, we must stop looking outward at clocks and equations and stars and turn instead to the one place we have not yet examined, the strange and intricate machinery that builds your sense of a moving present out of the still material of the world. We must look behind your own eyes. The first thing to understand about the sense of time is that there is no single organ in your head that measures it. You have an eye for seeing and an ear for hearing, dedicated instruments for light and sound, but there is no clock for time, no one place you could point to and say, there, that is where the seconds are counted. Instead, your sense of time is stitched together from the activity of many parts of the brain working together, a distributed and improvised business, and this turns out to matter enormously, because a sense assembled from many pieces is a sense that can be fooled and stretched and edited and even, in a way, invented. The felt flow of time is not read off some internal chronometer. It is built moment by moment by a brain doing its best to make a coherent story out of a flood of signals that do not even arrive in order. Consider first the very idea of the present, the now you began the night so sure of. It feels like an instant, a knife edge, a single dimensionless point where the future becomes the past. But the present you actually experience is nothing so sharp. The American psychologist William James, who wrote one of the founding works of the science of the mind in the year 1890, gave this experience present a lovely name. He called it the specious present, specious meaning seemingly but not truly what it appears. James saw that the now we live in is not a razor-thin instant at all, but a small smear of duration, a short window a few seconds wide, in which a little of the just past still lingers, and a little of the about to be is already anticipated. You can feel this if you listen to a spoken sentence or a line of music. To hear a melody at all, you must hold several notes together in your mind at once, the note just gone still sounding faintly, while the present note plays and the next one leans in. If your now were truly a single instant, you would hear only one isolated tone, with no melody, no phrase, no sense at all. The fact that you can hear a tune means your present is thick, not thin, a held breath of a second or two rather than a vanishing point. The now is already a construction, already the brain gathering a spread of time into a single felt moment. And the brain does far more than thicken the present. It actively edits the order and timing of what you experience quietly, behind the scenes, so smoothly that you never notice the seams. Here is something strange and true. The signals from your senses do not all arrive at the brain together. Light is fast and sound is slow, so when someone speaks to you from across a room, the sight of their lips moving reaches your eyes before the sound of their voice reaches your ears, and the nerve signals from your senses travel at different speeds too, and take different amounts of time to be processed once they arrive. If you experienced each signal the instant your brain finished with it, the world would be a jumble, sight and sound and touch all slightly out of step. Instead, your brain waits. It holds the signals, lines them up, and serves you a single, coherent, unified moment in which the lips and the voice match, in which the tap you feel and the sight of the tapping finger agree. The now you experience has been assembled and smoothed and synchronized, delivered to you a fraction of a second late, already edited into tidiness. The present you live in is, Quite literally, a story the brain tells slightly after the fact. There are moments when this editing becomes visible, small cracks through which you can glimpse the machinery. Look at a clock with a ticking second hand, glance away, then flick your eyes back to it, and there is an odd sensation that the first tick after your gaze lands takes a little too long, that the hand hangs a moment before it moves on. This is a real and repeatable effect. When your eyes make a rapid jump from one point to another, the brain briefly blinds itself during the motion, because a smeared image of the world swinging past would be useless, and then, to hide the gap, it stretches the first thing you see afterward backward in time to paper over the blank. You're shown a slightly false version of when the tick happened, and you never suspect a thing. Your brain is not a passive recorder of time. It is an active editor, cutting and stitching and backdating, all in the service of giving you a seamless, sensible now to live inside. If the brain can stretch a single tick, it can stretch far more. Many people who have lived through a sudden accident, a fall, a near miss, report that time seemed to slow down, that the world moved as if through honey, that they had strange stretches of clarity in what could only have been a second or two. For a long time it was tempting to think that in danger the mind somehow speeds up, sampling the world faster, seeing more per second like a high-speed camera. Careful experiments suggest something subtler and more revealing. The neuroscientist David Eagleman devised a way to test this by having volunteers experience genuine, controlled fear while trying to read a rapidly flickering display, on the reasoning that if their perception had truly sped up, they should be able to read numbers flashing too fast to see under ordinary calm. They could not. Their perception had not sped up at all. What had happened was that in the grip of fear, the brain laid down memories far more densely than usual, recording the frightening moment in unusual richness of detail. And because we judge how long a stretch of time was, after the fact largely by how much we remember happening in it, that densely recorded moment felt, in memory, as though it had lasted far longer than the clock would say. Time did not actually slow. The memory of it swelled, which tells you something profound. Much of what you call the length of a moment is not measured as it happens. It is reconstructed afterward from the thickness of the memory it left. Your sense of duration is a kind of remembering, not a kind of measuring. This same insight unlocks one of the most familiar mysteries of a human life, the way time seems to accelerate as you grow older. A summer in childhood felt endless, a slow, golden age, while the years of adulthood seem to blur past faster and faster, a week gone before you have taken its measure. Part of this is simple proportion. To a child of 5, a single year is a fifth of everything they have ever lived, a vast slice of the whole. To a person of 50, a year is a 50th, a thin sliver against the great mass of accumulated life, and so it weighs less and passes lighter. But there is more to it, and it comes back to memory and novelty. When you are young, almost everything is new, and novelty makes the brain record richly, densely, the way fear does, so that early life is packed thick with vivid first times and lays down a heavy weight of memory that, looking back, feels long. As you age and the world grows familiar, days fall into routine. The brain records less because less is new, and stretches of time leave only thin memories behind, so that in the rear view they seem to have flashed past in an instant. Time speeds up as we age not because the clock changes, but because the density of what we notice and store thins out. The felt length of your life is written in the ledger of memory, and that ledger fills fastest when the world is strange to you. Underneath all this felt, edited, remembered time, the body also keeps a slower and steadier kind of time that you never consciously sense at all, and it is worth knowing about because it shows how many different clocks are ticking inside you at once. Deep in the brain, just above the place where the nerves from your two eyes cross, sits a tiny cluster of cells that acts as the body's master timekeeper. It keeps a rhythm close to 24 hours, and each morning the light entering your eyes nudges it back into step with the turning of the earth, so that it can quietly conduct the great daily orchestra of your body, the rise and fall of your temperature, the release of the hormones that make you sleepy at night and alert by day, the whole tide of wakefulness and rest. This is a real clock, biological and chemical, running whether you attend to it or not, and it is completely separate from the vivid felt now we have been exploring. You are in truth full of clocks, some fast, some slow, some conscious, most not, all of them counting in their own way, and the smooth single stream of time you seem to experience is stitched together over the top of all of them, and that felt stream can be stretched and squeezed by the smallest things. Show a person a steady row of identical shapes, then slip one odd shape in among them, and that odd one will seem to linger on the screen noticeably longer than the others, though everyone was shown for exactly the same span. Novelty swells time, familiarity shrinks it, moment by moment, just as it does across a whole life. Fear stretches a second, as we have seen, but so does boredom in its own way, the empty minute that will not end because there is nothing to fill it, and so nothing to measure it by. And absorption does the opposite, folding hours into what feels like a handful of minutes so that time flies, as we say, when you are lost in something you love. Even your body heat plays a part, for when you are feverish and warm, your internal counting tends to speed up, and time outside seems to crawl by comparison. Every one of these is a small proof of the same large truth. There is no fixed, faithful clock inside you reading off the real rate of time. There is only a brain, estimating, guessing, constructing, building a sense of duration out of attention and novelty and memory and mood, and handing you the result as if it was simply how fast time is going. The felt flow is not measured, it is made. Picture then what the brain is truly doing with time. It is taking a flood of signals arriving out of order, gathering them into a thick present a second or two wide, editing and backdating and synchronizing them into a seamless flow, judging their duration after the fact by the weight of the memories they leave. And out of all this improvisation it produces the single most convincing experience you will ever have. The smooth, moving, undeniable sense of now sliding forward into then. It is a little like the way a film works. A film is nothing but a run of still photographs, each frozen, each timeless, shown one after another fast enough that your mind fuses them into fluid motion. There is no movement in any single frame, and there is no movement in the strip of film, which is just a row of stills. The motion exists only in you, in the brain that stitches the frozen frames into a living flow. And what our whole night has been circling toward is the possibility that the flow of time itself may be exactly this kind of thing, a smooth motion your mind manufactures from a world that, frame by frame, does not move at all. Notice too where your sense of the direction of time comes from, the difference between past and future that feels so absolute. You do not remember the future, you remember the past. And why? Because memory is a record, a physical trace laid down in the brain, and laying down a record is exactly one of those entropy-increasing, order-consuming processes that the second law governs. You can hold records of the low-entropy direction, the past, because forming a memory rides the same slope from order to disorder that gives time its arrow in the wider world. The reason your now feels poised between a fixed, known past and an open, unknown future is that the past has left its marks in you, and the future has not yet done so. Even the felt asymmetry of time, the deepest seeming difference between behind and ahead, turns out to be tied to the arrow of entropy and to the brain's role as a keeper of records. The mind's construction of time and the physics of time are not two separate stories after all. They are threaded together at the root. So the face of time behind your eyes gives us the boldest answer yet to the question we began with. The flowing now, so far as we can tell, really is something the brain builds. Not fakes, not hallucinates in the dismissive sense, but constructs, actively and continuously, out of signals and memories and the smoothing of a busy mind. The passing of time appears to live on your side of the glass in the watcher, just as the missing flow in the physics suggested it must. And yet, and here honesty pulls us up short, we cannot simply declare that time is only in our heads and be done with it, because the brain is not building its sense of time out of nothing. It is building it out of real events, in a real order, riding a real arrow of entropy, in a universe whose deepest description we have not yet finished writing. The construction in your head is answering to something out in the world, and that raises a question that physics and philosophy have argued over for a century, gently, without resolution. A question about whether the past and the future are as real as the present, or whether only the now truly exists. That argument is genuinely open, and it is the next face of the stone we must turn. There are roughly two great pictures a person can hold about the reality of past and future, and thoughtful people have held each of them, and physics has leaned on the debate without settling it. The first picture is the one that matches everyday feeling, and it is called presentism. On this view, only the present moment is truly real. The past was real once, but is gone now, vanished, existing only in traces and memories. The future is not real yet, not out there waiting, but truly open, unmade, coming into being moment by moment as the present rolls forward. On this picture, reality is a thin, bright edge, the now, and it moves. And the moving of it is the flow of time made real. It is the view most of us live by without ever naming. The sense that this moment is where existence happens and the rest is either wreckage behind or possibility ahead. The second picture is very different, and it is called eternalism, or often the block universe. On this view, all moments are equally real. The past has not ceased to exist, and the future is not waiting to be created. They are simply elsewhere in time, exactly as distant places are elsewhere in space. All of them there, all of them real, the whole four-dimensional block of history and future laid out at once. On this picture, the moment of your birth and the moment of your death, and this very moment of listening all exist together with equal reality, differing only in their position along the dimension of time, the way two cities differ only in their position along a road. The now is not special in any deep way. It only feels special to whoever happens to be at it. The way here feels special to whoever happens to be standing there, though every place is a here to someone. On the block picture, time does not flow at all. The sense of flow is, once again, something added by minds moving through the fixed landscape, not a feature of the landscape itself. You might think this is a question no experiment could ever touch, a matter of pure philosophy. But relativity, that great unsettler of the shared present, put a heavy thumb on the scale and it pressed toward the block. Recall what relativity showed us, that whether two separated events happen at the same time depends on how you are moving, that there is no universal now, that different observers slice the events of the world into present and past and future along different angles. Now think about what that does to presentism. Presentism says only the present is real. But if two people moving differently disagree about what is present, about which distant events are happening now, then whose present is the real one, the one that gets to count as reality? Relativity says there is no privileged answer, no single correct now, no observer whose slicing is the true one. And if no one's present is specially real, it becomes very hard to hold that only the present is real, because there is no single present for everyone to share. Two thinkers, working independently in the middle of the last century, a physicist named Cornelius Rietzdyk and the philosopher Hilary Putnam, sharpened this into a formal argument. If you take relativity seriously, they showed, and if you accept that events others count as present are as real as your own present, then by chaining together the presence of different observers you are led, step by step, to conclude that all events, past and future alike, are equally real. The block, not the moving edge. Relativity does not prove eternalism beyond all doubt, but it fits the block far more comfortably than it fits the flowing now. Picture the difference this way. Presentism is like a single lit candle carried down a long dark hallway, and only the small circle of light around the flame exists, the rest of the hallway coming into being as the candle reaches it, and falling back into nothing as the candle moves on. Eternalism is like the whole hallway standing there complete in the dark, every doorway and every step already present, with the candle merely revealing to a walker what was there all along. On the first picture, the walking creates the hallway. On the second, the hallway was always there, and only the walker's small light moves. Relativity, with its refusal to grant any single moment the privilege of being the real present, whispers that the hallway is probably all there, and that the moving light of the now belongs to us, the walkers, and not to the corridor of time itself. The very man who had dissolved the universal now, the young clerk grown old, seems to have taken a quiet comfort from this picture near the end of his own life. When a dear friend of his, a companion of his earliest days in physics, died just a short while before he himself would, he wrote a letter to the grieving family, and in it he set down a line that has been remembered ever since. For those who accept the physics, he wrote, the distinction between past, present, and future is only an illusion, however stubborn and persistent that illusion may be. He was consoling people in mourning, and the consolation he reached for was the block, the sense that his friend had not been erased into nothingness, but was still there, at his own place in the fixed landscape of space-time, as real as he had ever been, merely elsewhere in time. It is a striking thing that a man facing the loss of a friend and the nearness of his own death should find solace in the idea that time does not truly flow, that no moment is ever really lost because no moment ever really passes. I offer it to you not as proof of anything, for one physicist's comfort settles no debate, but as a reminder that these are not cold or empty questions. How real the past is, whether the people and moments we love are gone or merely elsewhere, touches the tenderest places in a human life. And it is worth knowing that some of the deepest minds who have thought hardest about time have come away believing that nothing that has ever been is ever wholly lost. And yet I want to be careful and honest here, because this is one of the places where physics does not hand us a settled answer, and it would be a small betrayal of you to pretend otherwise. The block universe is the more natural reading of relativity, and many physicists hold it, but it is not forced upon us with the finality of a measured fact. There are thoughtful physicists and philosophers who resist it, who argue that relativity constrains how we can talk about simultaneity without fully deciding the metaphysics of past and future, who develop careful versions of presentism, or a middle view called the growing block, in which the past and present are real and fixed but the future is not, the block of reality growing at its leading edge as new moments come into being. These are live positions, argued in good faith by serious people. What we can say plainly and with confidence is the physics. There is no universal present. Simultaneity is relative. The equations describe a fixed pattern of events with no flow built in. What we cannot yet say, what remains genuinely and beautifully open, is whether that means the future already exists in the same full sense the present does, or whether reality is somehow thinner and more open than the block suggests. Physicists and philosophers do not agree, and that disagreement is not a gap to be embarrassed by. It is one of the deepest unfinished conversations in human thought, and you are welcome to lie here and hold both pictures in your mind at once, the candle and the hallway, and feel no urgency to choose. To press further into it, we have to leave the smooth world of relativity behind and enter the flickering, uncertain, granular world of the very small, where time behaves more strangely still, and where the clean picture of a fixed block begins at its edges to tremble. When you shrink your attention down to the scale of single atoms and the particles inside them, the world stops behaving in the solid, definite way it does at the scale of cups and pendulums, and begins to behave like something far stranger and more dreamlike. Down there, a particle does not have a definite position until you look. Instead, it is described by a spreading wave of possibility, a mathematical object that holds all the places the particle might be found, each with its own likelihood, all at once. This wave, called the wave function, is the central character of quantum mechanics, and its behavior is governed by an equation written down in the 1920s by the Austrian physicist Erwin Schrödinger. His equation is one of the most successful in all of science, predicting the behavior of atoms and molecules and light to extraordinary precision, underlying the chemistry of every living thing and the workings of every device you own. And when you look at how it treats time, you find something that should stop us in our tracks given everything we have turned over tonight. Schrödinger's equation, which describes how the wave of possibility changes, is smooth and continuous, and like the great laws before it, perfectly reversible in time. Left to itself, the quantum wave evolves in a stately, deterministic way, running just as lawfully backward as forward, carrying no arrow, marking no present. So far, the quantum world only deepens the mystery we have been living with. But quantum mechanics has a second act, and it is here that time does something peculiar that it does nowhere else. When you measure a quantum system, when you look to see where the particle is, the spreading wave of possibilities appears to snap suddenly and sharply into a single definite outcome. The particle, which was a smear of maybes, is abruptly found in one place. This apparent snap, often called the collapse of the wave function, looks nothing like the smooth, reversible evolution of the equation. It looks sudden, one way, and tied to a particular moment, the moment of measurement, a now at which possibility becomes fact. For the first time, we seem to have found, buried in the quantum act of measurement, something that singles out a present and points a direction. But I must be careful and honest, because what that snap actually is may be the single most argued over question in all of physics, and no one can tell you the answer as settled fact. This is the famous measurement problem, and physicists have proposed strikingly different pictures of what is really going on, none of them yet proven, all of them consistent with everything we have so far seen in the laboratory. In one family of views, the collapse is a real physical event, a genuine snapping into one outcome, and the present moment of measurement is a real feature of the world. In another, associated with the idea of many worlds, there is no collapse at all, only the smooth reversible equation, and every possible outcome actually happens, each in its own branch of a vast and ever-splitting reality, so that the snap you seem to see is only the branch you find yourself in. In still others, hidden details we cannot access guide the particle to its outcome all along. These pictures disagree profoundly about whether there is any real collapse, any real singling out of a now, any genuine arrow in the quantum world, or whether all of that is once again something contributed by us, the observers embedded in the wave. Physicists do not agree on which picture is correct. What looks, at first, like the quantum world finally handing us a real flowing present may be, depending on which interpretation is true, either exactly that or one more illusion of the observer. It is an open question, and a deep one. Physicists have at least come to understand part of why the snap seems so sharp and so irreversible, even if they still argue about what it ultimately means. A quantum system is almost never truly alone. The moment it touches anything else, a stray particle of light, a molecule of air, the atoms of a measuring instrument, it becomes entangled with that vast surrounding world, its delicate wave of possibilities spreading out and mingling with everything around it. This spreading into the environment, which physicists call decoherence, happens with staggering speed for anything larger than a single particle, and its effect is to scramble the fragile overlap between the different possibilities so thoroughly that they can no longer show their quantum nature to us, no longer interfere, no longer behave like a smear of maybes. For all practical purposes, the system then looks as though it has settled into one ordinary definite outcome, and this is why you never see a chair or a cat or a coffee cup hovering in a blur of several states at once. The largeness and warmth and connectedness of everyday things drowns their quantum strangeness almost instantly in the sea of their surroundings. But notice what decoherence does and does not do. It explains why the possibilities stop interfering and why the world looks classical and settled to us. It does not, by itself, explain why you end up experiencing this particular outcome rather than that one, why your now contains this result and not the other. That last step, from a spread of possibilities that no longer interfere to the single, definite thing you actually find, is exactly where the interpretations part ways and where the mystery of the present, the moment where one possibility becomes your reality, still stubbornly lives. We have learned a great deal about the shape of the puzzle. We have not solved it. There is another quantum strangeness about time worth resting on, because it reveals how differently the small world treats time from the way relativity does. In quantum mechanics, position is something you measure, and observable with its own uncertainty, but time is not treated that way at all. Time enters the equations as a smooth external parameter, a fixed background marching along outside the system, the same for everything, not something the system itself possesses, or that you measure with an instrument pointed at the particle. This is a strange asymmetry, because relativity had gone to such trouble to weave time and space together into a single fabric, and here, in the other great theory, they are split apart again, space made uncertain and personal, while time is left rigid and universal and external. The two deepest theories we have hold two different and incompatible pictures of what time is, and that quiet contradiction sits at the heart of physics, like a splinter no one has been able to remove. Consider how deep the difference runs. In the quantum world, everything you can measure comes with an uncertainty, a fuzziness, a range of possible values, position and speed and energy all included. You point an instrument at a particle and ask where it is, and the answer comes back as a spread of maybes. But you never point an instrument at a particle and ask what time the particle itself is. Time is not something the particle carries and you read off. Time is the label on the outside, the reading of a clock in your laboratory, the same for the whole experiment, a smooth external number ticking along in the background against which everything else is measured. In relativity, time had become personal, bending and stretching, belonging to each observer and each place. In quantum mechanics, time is impersonal again, a rigid universal parameter standing outside the quantum fuzziness rather than sharing in it. So the two theories do not merely describe time differently in some technical way. They disagree about what kind of thing time is at the most basic level, whether it is a flexible participant woven into the fabric of events or a fixed stage on which events are painted. Both theories are magnificently, precisely correct in their own domains, tested to staggering accuracy, and yet they cannot both be telling the final truth about time, because their pictures of it simply do not fit together. Somewhere beneath both of them there must be a deeper account, one in which this contradiction dissolves, and every attempt to find that deeper account leads us, as we're about to see, into water stranger than either theory alone. Even so, time and energy in the quantum world are bound together by one of the most famous relationships in physics, a cousin of the uncertainty principle first drawn out by the German physicist Werner Heisenberg. It says roughly that energy and time cannot both be perfectly sharp at once. A process that happens over a long, leisurely stretch of time can have a very precise, well-defined energy. But a process confined to a very brief instant has an energy that is inherently blurred, spread out, uncertain. Think of the whir of a hummingbird's wing. Watched over a long moment, the wing has a steady beat, a definite hum, a clear pitch you could name. But try to catch it in a single frozen instant, to pin the wing to one sharp point in time, and the steady hum dissolves, the pitch smears away, and you're left with a blur that could be almost any note. The sharper you make the moment, the fuzzier the energy becomes, and there is no way around it, for the two are locked together by the very structure of the quantum world. Time, even here, refuses to sit still and be simple. It is entangled with energy, blurred at short scales, treated as a background it should perhaps not be, and it will not settle into the clean fixed thing our intuitions want it to be. Take a slow breath, and let the strangeness of all this rest lightly on you, because we have arrived at a genuine frontier now, the edge of what physics can currently say, and there is no shame in the fact that the ground grows softer here. We have seen time as a counted interval, as a relative slicing of events, as a directionless law, as a slope of entropy, as a construction of the brain, as a fixed block or an open edge, and now as a quantum background that behaves quite unlike space. Every one of these faces has chipped away at the idea that the flowing present is a simple, fundamental feature of the world, and the deepest crack of all opens when physicists try to do the one thing they have never quite managed, to bring the two great theories together, to make gravity itself a quantum thing. Because when they try, in one of the most serious attempts ever made, time does not merely become strange, time disappears. To feel why this is such a crisis, you have to hold in your mind how differently the two great theories treat time and see that the difference cannot survive their union. In the theory of gravity, time is not a fixed background at all. Time and space together form a flexible fabric, bent and stretched by mass and energy, running faster here and slower there, personal to every observer, part of the very thing that gravity shapes. Clocks near a heavy mass tick slower than clocks far away, and this too has been measured, so that even the flow of time in the ordinary sense is woven into the geometry that gravity governs. Time, in the theory of gravity, is dynamical, a participant, part of what changes. But in quantum mechanics, as we have just seen, time is exactly the opposite, a rigid external parameter against which everything else evolves, sitting outside the system, untouchable, fixed. Now ask what happens when you try to make a quantum theory of gravity, a theory in which the fabric of space-time itself, time included, becomes a quantum thing spread out into possibilities like everything else quantum. You're trying to quantize time itself. But quantum mechanics needs a background time to evolve against, an outside clock to march to. And if time itself is the very thing you are turning quantum, there is no outside clock left, nothing external for the quantum evolution to happen with respect to. The theory eats its own foundation. This is not a hypothetical worry. In the 1960s, two physicists set out to write down a quantum equation for the geometry of the entire universe, treating the whole of space-time as one vast quantum system. One was John Wheeler, an American physicist of enormous imagination, the same man who had given the world the vivid name black hole, a teacher who loved to push ideas to their breaking point and see what spilled out. The other was Bryce DeWitt, a careful and formidable theorist who did much of the hard mathematical labour of pushing the idea through. Together, around the middle of that decade, they arrived at an equation, now called the Wheeler-DeWitt equation, meant to describe the quantum state of the whole cosmos. And when they looked at what they had written, it contained a shock. The equation had no time in it. Where an ordinary quantum equation describes how a state changes from one moment to the next, this one described a state that does not change with time at all, because there was no time variable left for it to change against. The quantum state of the universe, as this equation describes it, simply is. It does not evolve. It does not flow. It is frozen, complete, timeless, all at once. DeWitt, by many accounts, did not much like the equation that bears his name, and one can understand why, for it seemed to say something almost impossible to believe, that at the deepest level, the level of the whole universe taken together, there is no time. Physicists have a name for the puzzle this opens, and they call it simply and honestly the problem of time. It is one of the great unsolved problems standing between us and a finished theory of everything. How can the fundamental description of the universe be timeless, when everything we experience, every heartbeat and every falling leaf, and every thought moving through your mind right now, is utterly drenched in time? I want to be as clear as I can about the standing of all this, because we are far out past the settled shore. Quantum gravity is not an established, confirmed theory. There is as yet no experiment that has tested these equations directly, no measurement that pins them down, and serious physicists pursue several very different approaches to uniting gravity and the quantum, of which this is only one. The Wheeler-DeWitt equation is a candidate, a signpost, a provocation, not a proven law. And physicists openly disagree about what its timelessness means. Some take it at face value and conclude that time really is not fundamental, that at the base of reality there is no time at all, and that this is one of the profoundest lessons the universe has offered us. Others suspect the timelessness is a sign that the approach is incomplete or being read wrongly, that time will return once we understand things better. No one can tell you tonight which of them is right, and this equation is only one road into the mystery. The effort to unite gravity with the quantum is one of the great unfinished labours of physics, and it is pursued along several very different paths, none of them yet confirmed by any experiment, each of them a serious attempt by serious people to reach beneath both of our great theories. What is striking, and what makes all of this worth whispering about tonight, is that so many of these paths, for all their differences, arrive at the same strange suggestion. In several of them, space and time are not the fundamental stage on which reality plays out. Instead, they are woven, emergent, stitched together out of something more basic that is itself neither spatial nor temporal. In some approaches, the smooth fabric of space-time is imagined as arising from vast networks of pure quantum relationships, a kind of underlying weave with no distances and no durations built in, from which space and time appear only when you step back and look at the whole. In others, the continuous flow of time is thought to emerge from countless tiny grains of happening, discrete events linked only by which gave rise to which, with the smooth river of time, a large-scale illusion laid over that granular foundation. I want to be careful and honest about the standing of all this, because it is the softest ground we will stand on tonight. None of these pictures is established. They disagree with one another. No experiment has yet reached down to test them. They may all be wrong, but their shared instinct is worth carrying with you into sleep, because it points the same way everything else has pointed. Again and again, when physics tries to reach the very bottom of things, time thins out, loses its flow, and begins to look like something that emerges rather than something that was there from the start. But sit for a moment with the possibility, the sheer strange beauty of it, that the equation might be telling the truth. Picture the fundamental state of the universe as a kind of map. A map of a river valley can show you every bend and every pool, every place the water goes, the whole course laid out complete on the page. What a map cannot show you is the current, the actual flowing of the water, the movement itself. The map holds all the structure of the river and none of its motion. What the Wheeler-DeWitt equation seems to whisper is that the universe, at its deepest level, may be like that map, holding the entire structure of everything that is, every relationship between every part, laid out complete and at once, with no current running through it, No flow, no passing, no time in the sense of something that moves. All the befores and afters would be there, in their fixed relations, exactly as every bend of the river is on the map. But the flowing between them, the movement from one to the next, the very thing you feel as the passing of your evening, would simply not be a feature of the map at all. It would have to come from somewhere else. And that leaves us with the most delicate and wonderful question of the entire night. If the deepest layer of reality is truly timeless, a frozen map with no current in it, then where does time come from? How does the vivid, flowing, undeniable river of your experience arise out of a universe that, at its foundation, does not flow at all? That question has no settled answer either, but there are ideas, careful and hopeful ideas, about how time might be born from timelessness, and they are among the most beautiful things physicists have dared to imagine. Suppose the boldest reading is right, and the universe at its foundation truly is timeless, a frozen map with no current running through it. That would leave us with a mystery so sharp it feels almost like a paradox. Here you are, soaked in time, watching one moment give way to the next, and yet the deepest layer of things is supposed to hold no flow at all. The question is how the river of your experience could rise out of a still and timeless sea. And physicists, rather than throwing up their hands, have offered some remarkably beautiful ideas about how time might be born from timelessness, how something we experience as fundamental might instead be a thing that emerges. I want to walk you through two of them, gently, and I want to keep flagging as we go that these are frontier ideas, hopeful and serious but not settled. The kind of thing thoughtful physicists propose and debate rather than the kind of thing measured and closed. The first idea grows out of the very science of heat that gave us the arrow of time. It was developed most fully by the Italian physicist Carlo Rovelli, working together with the French mathematician Alain Connes in the 1990s, and it goes by the name of the thermal time hypothesis. The thought behind it is subtle and rather lovely. We never deal with the universe in full microscopic detail. We cannot track every molecule, every particle, every tiny degree of freedom. We only ever know the world in a blurred, averaged, coarse-grained way, in terms of temperatures and pressures and large-scale states, the sort of description that throws away almost all the fine detail and keeps only the big statistical picture. Rovelli and Connes showed with some deep mathematics that once you describe the world in this blurred statistical way, a preferred notion of time emerges naturally out of the statistics themselves, a flow defined not by any external clock but by the thermodynamic state of the system, by the very blurring. On this view, time's flow is not fundamental at all. It is a consequence of our own limited, macroscopic, heat-based perspective on a world that, seen in full detail, would not flow. Time, they suggest, is what a statistical, entropy-bound creature like you experiences when it looks at a timeless world through the only lens it has, the coarse lens of heat and averages and ignorance. The flow of time and the flow of heat, on this picture, are the same thing seen from two sides. The second idea is stranger still, and to me one of the most quietly astonishing thoughts in modern physics. It was proposed in the year 1983 by two physicists, Don Page and William Wouters, and it explains how a universe that is globally, totally timeless, can nonetheless look, from the inside, as though it is full of flowing time. The secret is entanglement, that deep quantum connection by which two systems can share a joint state so intertwined that neither has a definite condition on its own, only the pair together. Page and Wouters asked us to imagine dividing the timeless universe into two parts, one small part that we will treat as a clock, and everything else. The whole thing, taken together, is static, unchanging, exactly as the timeless equation demands. Nothing about the total state ever changes. And yet they showed if the clock and the rest are entangled in the right way, then when you ask what the rest of the universe looks like for each particular reading of the clock, you find that it appears to change from one clock reading to the next. Relative to the clock, the rest of the universe evolves. Time is not something outside the system ticking along. Time is the relationship between the clock part and the everything else part, a correlation woven into a state that, as a whole, never changes at all. From inside, entangled with your clocks, you see a flowing world. From outside, if there could be an outside, the whole would be seen to be frozen and complete. Picture two dancers, perfectly in step, moving together to a music only they can hear. If you watch one dancer alone, you see them turning and stepping and swaying, full of motion and time. But the truth of what is happening is not in either dancer separately. It is in the relationship between them, in the way each step of the one answers a step of the other. You could read the time of the dance entirely from how the two of them stand in relation, without any outside beat at all, without any clock on the wall. The music, the external time, turns out to be unnecessary. The flow lives in the correlation, in the mutual answering of the partners. That, roughly, is what Page and Wouters proposed for the whole universe. There is no outside music, no external time. There is only the endless mutual answering of the parts of a static whole, and that answering, read from the inside by any part that serves as a clock, is time. What makes this more than a pretty story is that physicists have managed to build tiny model universes in the laboratory that behave exactly this way. Around the year 2013, a team of researchers in an Italian laboratory constructed a miniature version of the Page and Wouters idea using a pair of entangled particles of light, letting one photon play the role of the clock and the other play the role of the evolving universe. And they found precisely what the idea predicted. An observer who used the clock photon, who read time from inside the little system, saw the other photon change and evolve, saw time pass. But an observer who somehow stood outside the whole entangled pair, measuring only the joint state as a totality, saw nothing change at all, saw a static and timeless whole. The very same little universe was flowing from within and frozen from without, depending only on whether you read it from inside as a part or from outside as the whole. I want to be careful and not oversell this, because it is a small and simplified model, a toy universe of two particles built to illustrate a mechanism, not a proof that our own vast cosmos truly works this way. But it is a real demonstration that time can emerge from timelessness as a matter of perspective and entanglement, that a frozen whole really can contain a flowing inside, and that is no small thing to have shown with light on a laboratory bench. Underneath both of these ideas, the thermal one and the entangled one, there runs a single quiet conviction, and it is one of the oldest ideas about time ever argued over, now returning in modern dress. It is the idea that time is relational, that time is not a container the universe sits inside, not an empty stage that would still be there ticking away even if nothing ever happened, but rather nothing more than the order and relationship of changes themselves. On this view, to speak of time is only ever to speak of how one thing changes with respect to another. This hand of the clock against that position of the sun, this beat of the heart against that swing of the pendulum. And if nothing anywhere ever changed, there would simply be no time at all. Not empty time passing in the stillness, but no time, because time just is the pattern of change and nothing more. This is a very old quarrel. Centuries ago, when the modern picture of physics was first being built, there was a deep disagreement about exactly this. On one side stood the view that time is absolute, a true universal river flowing on its own, whether or not anything happens in it. On the other side stood a great thinker named Gottfried Leibniz, who argued fiercely that this was nonsense, that time could be nothing but the order of events, a way of describing their before and after, with no independent existence of its own. For a long time the absolute view held sway, carried by its towering success. But the strange road we have walked tonight, through relativity and entropy and the timeless equations of the very small, has led physics back, in a way, toward the older relational instinct. Time, more and more, looks not like the stage but like the dance, not the river but the flowing, not a thing that exists on its own but a thing that only exists in the relationships between changes. And if that is so, then time being emergent is exactly what we should expect, for a relationship is always something that emerges from the things related, real and important, and yet never a fundamental object in its own right. Both of these ideas, the thermal one and the entanglement one, point in the same gentle direction. They suggest that time is emergent, that it is not part of the deepest fabric of reality but arises from something more basic, from the statistics of heat, or from the entanglement of parts, or from the perspective of beings like us who are large and warm and made of many pieces and can only ever see the world in a blurred and partial way. And here we come to the word on which the whole reconciliation turns, the word I have been carrying toward you all night: emergent. Because the moment you hear that time might be emergent rather than fundamental, there is a temptation to hear it as a demotion, to think, then time is not really real, it was just in our heads all along, and to feel the whole rich river of experience reduced to an illusion. But that would be a mistake, and it would be exactly the wrong lesson, and to see why, we only have to look at something as ordinary and as undeniable as the warmth of your own body under the blankets right now. Reach for the simplest and most familiar of all emergent things, temperature, the warmth you feel this very moment. Temperature is real. No one lying warm in bed on a cold night doubts that warmth is real. It can be measured to great precision. It is the difference between comfort and danger, between liquid water and ice, between a living body and a still one. And yet here is the quiet marvel of it. No single molecule has a temperature. Temperature is not a property that any one particle possesses. What we call temperature is nothing but the average energy of motion of a vast swarm of molecules, jostling and colliding, and averageness is not a thing a single molecule can have, any more than a single person can have an average height. Temperature exists only in the crowd. It is a collective property, an emergent one, arising from the behaviour of many parts, meaningless for any part alone. If you shrank down to the size of one molecule and asked it for its temperature, the question would have no answer, and yet step back up to the scale of a body, a room, a cup of tea, and temperature is as real and as consequential as anything in the world. It burns, it soothes, it keeps you alive. Emergent does not mean unreal. Emergent means real at one scale and absent at another, real in the crowd and meaningless in the single part. And once you have the idea, you begin to see emergent things everywhere, real and undeniable and yet belonging only to the many and never to the one. Wetness is like this. A single molecule of water is not wet. Wetness is something water molecules do together, in their vast numbers, sliding over one another and clinging to your skin, and it has no meaning at all for one molecule alone, and yet no one lying in the rain would call wetness unreal. Solidity is like this too. The table beside your bed is almost entirely empty space, its atoms mostly gap, and no single atom is solid in the way the table is, and still the table holds your lamp and would stop your hand, as solid as anything you know, its solidity a collective fact that no part possesses by itself. Even something as simple as pressure, the push of the air exists only in the crowd, the summed drumming of countless molecules against a surface, meaningless for any single one. There is a lovely example in a traffic jam which can crawl slowly backward along a motorway, the dense knot of it drifting against the direction of travel, even though every single car within it is moving forward, so that the jam is entirely real, real enough to trap you in it for an hour, and yet it is made of nothing but forward motion, and exists only as a pattern in the many. A wave crossing a pond is the same, carrying its shape all the way to the far bank while no drop of water actually travels across, each drop only rising and falling in place, the wave real and moving, and yet nothing but a pattern passing through parts that stay home. Life itself, some would say, is such a pattern, a shape that persists while the very atoms composing it are swapped out again and again. All of these are real. None of them lives in the single part. All of them emerge. Now hold time up against that and feel how the whole night resolves. Perhaps time is real the way warmth is real. Perhaps the flowing present is not a fundamental feature of the deepest layer of things, not written into the frozen map of the universe, and yet is entirely real at the scale where you live, the scale of warm bodies and many particles and kept memories, and the long, slow slide of entropy. Perhaps the question we began with, is time real, or just in our heads, was posed as a false choice, and either that must exclude its or, when the truth is a gentle both, arranged in a particular order. The order of events is real, robustly, independently, out there in the world, settled beyond serious doubt. The direction from past to future is real, arising from entropy and from the strange low entropy beginning of things. But the flowing, the passing, the moving now, may be something that emerges only for beings like us, large and warm and forgetful and made of countless parts, riding the slope of disorder and keeping records of one direction and not the other. Not an illusion in the dismissive sense, not a mere trick, but an emergent reality, as real as warmth and as absent from the single molecule, a true feature of the world at your scale that simply is not there at the scale of the frozen equations. The river of time would then be neither purely out there nor purely in your head. It would be what the timeless world becomes when it is lived, from the inside, by something like you. Let that gather itself softly, because I think it is the most honest and the most beautiful answer we can offer, and it lets us come home at last all the way back to where we started, to the small, warm circle of the present you were so sure of at the beginning of the night. We have turned the stone of time all the way around now, face by face, and it is time to set it gently down and to say plainly what we know and what we do not, and then to let you rest. Here, then, is the honest accounting, the settled and the open and the perhaps forever hidden, laid out quietly side by side with no drama and no alarm. What is settled, tested, and beyond serious doubt is this. There is no single universal now that everyone shares. Time runs at different rates for things moving differently and for things sitting at different depths in gravity, and we have measured this with muons falling through the sky and with clocks carried on aircraft and satellites, and it is simply true. The direction of time, the difference between a fixed past and an open future, comes not from the fundamental laws, which do not care which way time runs, but from the relentless statistical climb of entropy from an extraordinarily ordered beginning, and the vivid, flowing, smoothly moving present that you experience is, to a degree that keeps surprising us, something your brain constructs, thickening a smear of duration into a felt now, editing and backdating your senses into a seamless story, judging the length of moments by the weight of the memories they leave. All of that is as solid as science gets, and none of it should trouble your sleep. It is simply the shape of the world. What is open, still argued over softly by honest and brilliant people, is whether the past and the future are as fully real as the present. The block against the moving edge, a question relativity leans upon but does not close, whether time is truly fundamental or instead emerges from something deeper and timeless, as the frozen equation of the whole universe hints, and as the ideas of thermal time and entangled clocks try to explain. What the snapping of a quantum measurement really is, and whether it marks a real present or only the branch we find ourselves in. These are not settled, and anyone who tells you they are settled is telling you a story rather than the truth. Physicists do not yet agree, and their not agreeing is not a wound in our knowledge but a living edge of it, the place where the next understanding will one day grow, and there may be, beyond even these open questions, something that stays hidden for as long as we last, the simple fact that we can never step outside of time to look at it from without, because every looking, every thought, every act of knowing is itself a thing that takes time, so that a creature made of time may never fully see time whole, the way an eye can never quite turn to see itself. There is something fitting in that, and even something consoling. Of all the things we have ever tried to understand, time may be the one we are least able to step outside of because we are not merely observers of time but are ourselves made out of it, our thoughts unfolding in it, our very selves stretched across it from one moment to the next. To ask a being like that to see time plainly is a little like asking a wave to step out of the water and look back at the sea. And yet look how far we have come even so, hemmed in as we are. We have measured time bending under speed and under gravity. We have traced its arrow back to the order of the first dawn. We have watched our own minds building the now, moment by moment, out of memory and attention. We have followed the equations down to a place where time itself grows quiet and may vanish, and we have found gentle, serious ideas for how it might be born again out of that stillness. That is no small journey for a creature that cannot even turn to face the thing it studies. We may never see time whole, but we have seen a great deal of it sideways by its effects, the way you can know the wind by the bending of the grass, and now come back, softly, to the beginning. Come back to that small pool of lamplight you were standing in when the night began, the single lit circle of the present with the long unlit corridor of past and future, running away in both directions. You were so sure of it then, so certain that the now was the last thing you would ever doubt. And here is the gentle turn at the very end of it all. You were right to be sure, and yet the now is not quite what you thought. It was never a place you were standing, a spot on some universal corridor where reality happened to be lit. It was always something you were carrying, a small warm light you bring with you, kindled by a brain stitching frozen frames into motion, riding a slope of entropy, reading time from the quiet answering of the world's entangled parts. The corridor, most likely, is all there, whole and complete in the dark, every moment of your life standing in its place needing no lamp to exist. And the light is yours, You do not stand in the present. You make it and you carry it, and wherever you go, it goes with you, this warm and moving now that the timeless universe becomes when it is lived from the inside by something as tender and as temporary and as real as you. So you can let the question go now, and let the certainty go with it, both of them, the sureness and the doubt, because you no longer need either one to rest. The now you are lying in, this very moment, warm under the weight of the blankets, is real the way warmth is real, and it is yours the way your own breathing is yours, and it asks nothing of you but that you be here in it, which you cannot help but be. The map of everything lies still and complete, needing nothing. And you, a small bright current moving through it, carry your little light a while longer into the dark and then gently let it dim and rest.